Introduction to Delta-Wye transformer connection. Part 6A. Voltage phasor diagram. So in this part, we'll talk about the voltage phasor diagram for the delta transformer connection. So basically, we're going to understand how this particular transformer diagram that's often found in nameplate, for example, we'll find out exactly how this is drawn and what this represents. So in part 2 of the video, we talk about the line-to-line voltage versus phase voltage relationship for both the delta connection as well as the Y or star connection. So we can measure the line-to-line voltage here. Line-to-line voltage between line A and line B. We'll see that that's essentially equal to phase A voltage. And similarly, when we measure line-to-line voltage between line B and line C here, that going to equal to phase B voltage here. And lastly, when we measure between line C and line A, it's equals to phase C voltage. So in this video, we're going to further talk about the voltage quantities on the delta side. Now to begin, let's clarify something. So the delta has no ground, but there is ground somewhere in our source here. Some generators in our source is tied to the ground, and that ground is the reference for this transformer. So we're going to assume it's this particular connection. So we know what the ground is, and we know that this ground is for the source, and we know that this ground is in the reference to this particular delta connection. So now what I'm going to do is I'm going to connect this ground to the Y. So I already connected it here, and I'm going to say that it's all the same ground. Now that I have established, I have the same reference quantity established. What I'm going to say is that the voltage across line A and this ground point here, so I'm gonna call this voltage VAG here, VAG. I drawn arrows to indicate it more clearly. And for VBG, this is measured across line B and the ground. And lastly, VCG is the voltage across line C and the ground. Now, the trick to understanding voltage phasors for delta connection is being really rooted in understanding of VAG versus VAB or phase voltage A. So VAB is the voltage across line A and line B, which is essentially equal to phase A voltage here. So we're talking about the difference of understanding phase A voltage versus VAG voltage. So oftentimes this VAG quantity is also called VAN, also referred as the reference quantity. So that's it for part 6A. Thank you for watching. So introduction to Delta-Wye transformer connection, part 6B. In this part, we're going to continue our discussion on the voltage phasor diagram for the delta transformer connection. So in part 6A, we set up our voltage phasor and we define VAG, VBG, and VCG. So we also said that there is a difference between VAG versus VAB or the phase A voltage. And that is the key to understanding voltage phasor for delta connection. So let's start. So VAB, which is the voltage across line A and line B, is equal to the phase voltage A, which is across winding A. That is also equal to VAG minus VBG, which makes sense, right? So VAG is which is the voltage across line here, and ground. And VBG is where the voltage cross line B and ground. So the voltage across line A and line B essentially equal to the voltage across line A and ground minus the voltage across line B to ground here. So next, let's evaluate these equations. So I've set something up already. So the first thing we're gonna do is that we're going to define our phasor value. It's VAG, VBG, and VCG. So I'm going to choose a value for VAG is equals to 2400 volts at 0 degrees. And for VBG, also 2400 volts at 240 degrees. And VCG, 2400 volts at 120 degrees. So this is a balanced setup three-phase voltage. So I'm going to call this phasor VAG because we defined it right. So VAG is at 0 degrees, and 0 degrees is in our reference line, right? So VBG is at this phasor, or this is the VBG, and the last one is our VCG, which is placed here. So right here is an ABC phase rotation. This is an ABC counterclockwise. This is an ABC phase rotation. Now, we said on our equation that line-to-line voltage across line A and line B, which is essentially voltage across our phase A winding for a delta connection, is equal to minus VBG. There. So here is our VAG. Right here, we're going to perform the head to tail method and subtract VAG minus VBG. Here, I'm going to subtract this. So first, I'm going to create a visual representation. So now that we have a visual representation, so if we relate VAG to VAB, we have to shift VAG by 30 degrees in counterclockwise. So if we take VAG now, we have to shift VAG by 30 degrees in the counterclockwise direction. And then we have to multiply it or stretch it by 1.73 or square root of 3, so it overlaps VAB. So which means that VAB is equals to square root of 3 times VAG and rotated by 30 degrees here. So we are doing this to understand the relationship between VAG and VAB, because that's what's going to help us understand the voltage phasor diagram for the delta connection. So that's it. Thank you for watching. Please comment and subscribe. Introduction to Delta-Wye Transformer Connection, Part C6. In this part, we're going to continue our discussion on the voltage phasor diagram for delta transformer connection and explain what this means. Okay, so in Part 6b, we concluded that VAB, which is this voltage phasor here, is equal to VAG, which is this voltage phasor here, rotated by 30 degrees and then multiplied by the square root of 3. So, mong equal ani is VAB. So, isuwat nato dire, VAB square root of 3 times VAB rotated by 30 degrees. I'm going to extend the concept to evaluate VBC and VCA. And that's going to look something like this. So, this phasor is negative VCG. And the phasor here is VVC. And we're going to say, i-rotate nato siya in 30 degrees in counterclockwise direction. And then we multiply by the square root of 3. Tapos we're going to equal, and that's going to equal to VBC. Similarly, we're going to do the same thing with VCA. VCA here is negative VCG. So we take VCG, rotate it by 30 degrees in counterclockwise direction, then multiply by the square root of 3 equal, and this will equal to VCA, which is this phasor here. Now, we have line-to-line voltage and as well as line-to-line voltages represented in our phasor diagram. So let's zoom out here and verify this. So remember, VAB is the voltage across two lines, line A and line B. VBC is the voltage across line B and line C. VCA is the voltage across line C and line A. And VAG is the voltage across line A and ground. And VBG is the voltage across line B and ground. And VCG is the voltage across line C and ground. Now notice that in part 6a, we said that line-to-line voltage across line A and line B is equal to phase A voltage. Now, if you're having a hard time recalling this, nato yung mga video na sa link, so, at sunod, i-label natin ang phasor diagram. So, remember, VAB is equal to V phase A. VBC is equal to V phase B. So, VCA is equal to V phase C on the high voltage side. Now that we've drawn this, we are at the point we can actually talk about the type of phasor diagram. We find it in transformer nameplates as well as engineer drawings. But before we go there, if you haven't already subscribed, click the button here. Okay, so let me clarify one thing. We said that this is VAB or V phase A, which is the voltage across line A to B, which is the same voltage across phase A winding. Now, since we represented the side as the polarity side of our winding, we're going to represent the polarity side by putting a dot here. For this phasor, this side is the polarity side. This is for phase A winding. And we're doing this just to get a visual. Right here, polarity side, and this right here is the polarity side. I'm going to remove some things that we don't really need, so to make this process as simple as possible. Okay, so this is what we do. This is where the magic comes from. I'm going to explain this little by, just bear with me and watch what I do to change this phasor diagram to something like this. Transmit here. Alright, so this is what we have. Before I explain how this works, let's just move it to the left hand side so we have a comparison. Okay, so first of all, this phasor diagram, right? This is what referred as the open form phasor diagram. And the right here is referred as closed form. So you might ask, what is the difference with these two? So now we are at this point, we're going to continue discussion in part 6D. Now, if you like this video, please like and subscribe. And thank you for watching. Introduction to Delta-Wye transformer connection, part 6D. So this is where we left off in part 6C. In this part, we're going to explain what this means and how this works. So now we said in our last video, this is often referred to as open form phasor diagram, and this one is referred to as a closed form phasor diagram. So open form versus closed form phasor diagram have their own advantages. Okay, so one way it works is that first of all, it's really helpful to label our phasor windings to get a visual understanding. Now this phasor here is VAG, and the point to this corner of this triangle, so I'm calling this A. And VBG is pointing to this corner, so I'm gonna call this B. And VCG is pointing at that direction, so I'm calling this C. The number one problem for closed form phasor diagram is that the shape of the triangle make us mentally think that the triangle represents line to ground A, B, and C voltage of the power system. And we clearly see na dili. So the triangle actually represents the line-to-line voltage of delta transformer connection here, and also equal to winding voltage. But our line to ground voltage are these inner phasors here. And that's one of the problem of this closed form, that it makes us think differently when we first visually. The second problem of this phasor is that when we look at this, we think the origin represents the neutral or the ground. And by inspection, the neutral is equal to the ground. The question comes up, is VAN equal to VAG? The last thing is number 3. The most confusing thing about closed form phasor diagram is why is VAB and VBC and VCA shown in this particular manner? It appears that the voltage drop for VAB, for example, the voltage drop should be from B to A, right? Because the arrow is pointing in this direction, so this voltage drop is from B to A, but it's written down is VAB. Something over here. When initially inspect it, it appears that voltage drop, this phasor, should be VAC because we start from A and go to C. But in reality, it's VCA. Some things over here. By inspection, it appears to be VCB, but in reality, it's VBC. So the voltage drop isn't as what we defined it. So the third reason why the closed form is so confusing, although it has its confusion, the content is very true and very correct. We just have to understand that this is telling us that if we compare that to the open form, everything becomes more clear. We know VAG, VAB, we know what's lagging and what's leading. So how much it's lagging or leading. So what's the benefit of closed for phasor diagram? So So the biggest benefit for this is it provides us and tell us how transformer windings for delta is connected. So let me repeat. This phasor diagram tells us how transformer windings for delta connection and how those windings are actually connected. This is the trick that I'm going to explain. This is what really neat about closed form phasor diagram. So you see this phasor here? We define this as phase A winding. And so we define this phasor here as V phase A, right? And we said that this side here is dotted side is the polarity side of V phase A. Look at what the polarity side of V phase A is connected to. It's connected to non-polarity side of V phase C. The polarity side of V phase A is connected to non-polarity side of V phase C. Now look at what the polarity side of V phase C is connected to. That's correct, to the non-polarity side of VB phase B. So the polarity side of V phase B is connected to non-polarity side of V phase A. Here. So let's back up. Let's compare it to the actual connection. We're saying that the polarity side of phase A is connected to non-polarities of V phase C. And the polarity side of V phase C is connected to the non-polarity side B. And polarity side of V phase B is connected to the non-polarity side of V phase A. And there you have it. So this closed form phasor diagram represents how the transformer is physically connected, and that's the most important thing that it tells us.